2. They're actually allowed 2. 2 sig figs, 3 sig figs. We need to know this to 4 sig figs. They should get 2 sig figs here. So we take this number and then round it to 1.5. So it's 1.5. All right. This is going into the duplicate number. The reason why the mole was defined in the way is to get something called the molar mass. So we have two things. We have the atomic slash, in other words, formula mass, which is atomic, molecular, or formula unit mass. And then we have something called the molar mass. And so we want that number pattern. So that's why we express it this way. And so let's take a look at some examples here. Carbon. Carbon will have something called the atomic mass. Atomic mass. Atomic mass of the average carbon atom is 12.01 U. And then we'll have something like the molar mass. Okay, this is U per carbon 12 atom, or carbon atom. This is the average carbon. The average carbon weighs 1201, but carbon 12 weighs exactly 12. And the molar mass would be 12.01 grams per mole of carbon atoms. This is the average carbon atom. Grams of carbon, U of carbon. H2O. H2O, we wouldn't refer to it as atomic mass, we'd refer to it as molecular mass because it forms molecules. So the molecular mass of H2O would be 18.02 U's worth of H2O per H2O molecule. And molar mass is the same though, because molar and molecular are not the same thing. Molar just refers to an Avogadro's numbers worth of anything. And so in that case, it would be 18.02 grams of H2O per mole of H2O molecules, per mole of the H2O molecules. NaCl. NaCl, we wouldn't call it atomic mass, we wouldn't call it molecular mass. Instead, we just call it the two words we can use. One, we would use formula mass. Formula mass. Formula mass is a very broad term used both for molar masses and there's another mass we can call it. We can call it the empirical mass. Empirical has two definitions. Chemistry. What are the two definitions for empirical? I mentioned them in the past before, but one is based on observation. And what was the second definition of empirical? Basic. Yeah, the most basic, the simplest unit. And so the simplest unit of a lattice of sodium chloride would be one formula unit, that is, that's one sodium and one chloride. And so here we would do the same thing, and then we'd have the molar mass of that. Now, this is a very common number. And so these numbers you find in tables. They're easy to calculate too. But if we go to NaCl, and look at Wikipedia, we'll have it here, like perspectives. Let's see, sodium chloride, also known as salt, is an ionic compound with the chemical formula NaCl, representing 1-to-1 ratio of sodium to chloride ions, with molar masses of 22.99 and 35.45 grams per mole, respectively. I don't know what are they talking about there. Okay, this is weird. But let's take a look at the Wikipedia entry. Let's see. Do that. Kind of somewhere there. So this is a typical number that we expect to see right off. So here, normally, since we don't work with U is so small, we typically work with grams, usually the molar mass that we see. It's 58.443 grams per mole. 58, we could easily calculate that to 2 digits, 58.443 grams of sodium chloride per mole of sodium chloride formula units, you say. Therefore, the formula mass must be what? Or the empirical mass must be what? Imperial mass, formula mass must be 58.443 U of sodium chloride for every sodium ion chloride formula unit. So one unit of that is going to weigh that many U. If I have a mole of those units, it's going to weigh that many grams. So this is typical. Let's see. Let's continue. Calculate the mass of calcium fluoride. All right, what is calcium? Ca plus 2. No, those tend to form cations. Fluoride? F minus. So the correct formula for calcium fluoride would be Ca. And so if we want the mass, okay, so they aren't specifying. Would this be a molecular mass here? Does calcium fluoride form molecules? No, we call it formula mass or molar mass. But typically we work with U, or typically we work with grams. And so calcium. Now the periodic table doesn't specify if it's U or grams, because you could use either. And so when we go to the periodic table, what's the average mass of calcium? When we look at the periodic table, this is the average mass. So one calcium weighs 40.078 U. But because of the way the mole was defined, we could say 1 mole of calcium weighs 40.078 grams. And so in order to save speed, we go 2 decimals. So I'm going to go 40.08. I'm going to round that. I know I told you about round off error and don't round until the very end, but when you have to calculate a lot of these molar masses, it becomes time consuming. And so in order to save time, we're going to sacrifice some accuracy for speed. And so I'm going to call this 40.08 grams per mole. Grams of calcium per mole of calcium atoms. And then we have 2 fluorines. It's going to be 2 times, what is fluorine over here? 18.998. So I'm going to go 2 decimal places. What should I call it? 18.998 would round to 19. Again, this is not what I told you to do, but to get the most accuracy, but we're sacrificing that. Because the advantage of doing it in 2 decimals is oftentimes you don't need a calculator to do it. So this is 40.08, and then 2 times 19 is just going to be 38.0. So this is going to give us 78.08 grams per mole. And so, in other words, I'm going to have 78.08 grams worth of calcium fluoride for every mole of calcium fluoride formula units. Formula units. Okay, they did the same thing, but they're not consistent. I'm going to be consistent. I'm always going to go 2 decimal unless it's hydrogen, atomic hydrogen, or molecular hydrogen. So the convenience of the mole is, I mean, even if you have a dozen atoms, if you had a dozen carbon atoms, you wouldn't even be able to see it. And so this is 6.022 times 10 to the 23rd worth of iron atoms. It weighs 55.85 grams. A mole of aluminum weighs 26.98 grams, and that would be a mole of atoms. A mole of atoms would be Avogadro's numbers worth of atoms. 6.022 times 10 to the 23rd. This is a mole of mercury. It's 200.6 grams. This is a mole of sodium. Sodium metal looks weird. This is a mole of copper. Now we have some compounds. These are the elements here. This is a mole of copper sulfate. That's copper. What's the charge on copper? Is that the copper is a 1, 2, 2, 3, 2, 4? What is copper?
1, 2.
That's a 1, 2. And the charge on that copper, is it copper 1 or copper 2? You can tell by the anion. What is the anion there? It's SO4. SO4 you've seen before, right? SO4 is is that sulfate? What is sulfate? Is it 4 oxygen or 3 oxygen? 4 oxygen. What's sulfate? What's the charge on sulfate?
4. 1,
Maybe you need to figure out. What's the charge on sulfate? 2. Yeah, right. Let's go. Silicate's 4, 3, 2. Sulfate's 2. SO4 2 minus. Therefore, that copper must be copper plus 2. Because we have 1 copper, 1 sulfate. It's a good balance it out. This is copper 2 sulfate, and then with applied waters, what we do is these waters get incorporated in. You see, it's not wet. The waters get incorporated in the crystal lattice itself, like a sponge, and so kind of a damp sponge. So it's still solid. So this is called copper 2 sulfate pentahydrate. Called the waters of hydration. So this is hydrated. We could also have dehydrated. For example, this is dehydrated oxalic acid. This is hydrated oxalic acid. So dehydrated stuff is shown here. C2O2, something weird. H2C2O4. That's correct. And then this is hydrated. Hydrated means a little bit of water gets trapped in there. How much water gets trapped in the crystal lattice depends on the crystal lattice itself. These waters get stuck in the spaces. Okay, this is a mole of copper 2 sulfate pentahydrate. It weighs 1 mole of this weighs 249.70 grams. 1 mole of this would consist of 6.022 times 10 to the 23rd copper ion, 6.022 times 10 to the 23rd sulfur, 4 times that, 4 times Avogadro's of oxygen, plus these 5 here, so 9 times that in oxygen, and then 10 times that hydrogen atoms. So this is a mole of various compounds and elements. Nitrogen, if you look at nitrogen, that's a mole of nitrogen in the back there. It's not very dense. It's a gas. You're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of compound do you measure out? And so what we're going to do is one of the most common conversions in chemistry. We're going to try to relate moles and grams. What we need is the molar mass. Molar mass does 2 things. So let's look at a molar mass like water. 18.02 grams of water per mole of water. So this is a very common conversion, moles to grams. Or if we flip this over, 1 mole of water weighs 18.02 grams. Then this is a gram to mole conversion. So 2 of the most common conversions in chemistry are mole to gram, gram to mole conversions. So we can relate the number of atoms. Remember we're talking about relating the number of atoms to weight, because we don't actually measure the number of atoms. We weigh it. We weigh it, and and then calculate how many atoms there are. So if we have, this is just dimensional analysis, 0.0360 moles. How many sig figs is that? Yeah, 3 sig figs. So barium chloride, what's the formula for barium chloride? Barium is what charge? 2 plus. Chloride is a. Barium. 2 plus. Chloride is a minus BaCl2 chloride. Do it. And how many grams of it are measured out? Well, what we need is a molar mass. So if we're going to do a mole to gram or gram to mole conversion, we've got to calculate molar mass. So this is a very common calculation. So we're calculating lots of molar masses. We're going to calculate lots of molar masses. It'd be nice to look them up, like on Wikipedia, but you can't on tests. You know, on the homework you probably can. Just look them up. But anyway, we got to first figure out barium. What's the mass of barium? And that, we just go to the periodic table and get it. We look at barium, 137.328. And so I call it 137.3. I'm not going to put units here because you have dual units for this. This could be either U per atom or grams per mole of atoms. This is dual unit. I'm not going to put the units until the end. In fact, I might not even put the units there until I'm ready to use it. Okay, then we have 2 chlorines. Chlorine actually I have memorized because it's very common, 35.45. Chlorine. And so this is going to give me 137.33, and then 2 times 35.45 is 70.90. So this is 3, 12, 8, 208.23. Now I can put the units. The 2 units I can have here are U per formula unit or grams per mole of formula unit. Well, in this case, we want grams per mole of formula unit. So here's mole of barium chloride formula unit. That's how many moles I have. So I know that there's going to be 208.23 grams of barium chloride for every mole of barium chloride formula unit. So save myself a calculation. Let's see what the book did. So first they got the, what did I call this? What do you call this? Is that the, yeah, that's the mass. This would be called the molecular mass. Does barium chloride form molecules or not? Barium chloride is an ionic compound. It doesn't form molecules. So we'd say that this is the formula mass. It's 208.23 U per formula unit. Or this would be the molar mass, 208.23 grams per mole of formula units. That molar mass could also be called a formula mass. No, numerically it's the same. They got 7.50. They rounded it, I didn't round it. You know, their emphasis on 6 gigs. They're using 4 6 figures for all the numbers, but my emphasis is this is addition, so I'm using 2 decimal places for all of it. And so we differ philosophy, me and the book have a different philosophy when it comes to calculating molar mass. Well, anyway, they got 7.50. I'm going to get a slightly different answer. So, what will my answer be? Because is it still the same? 0.036 times 208.23. 7.496. I'm allowed 3 sig figs, yeah. Which is 7.50 grams of barium chloride. Okay, now we're gonna add on one other type of conversion. And the next type of conversion that's common is using Avogadro's number. And so if we use Avogadro's number, n sub a, then we see that there are 6.022 times 10 to the 23rd of whatever per mole of whatever. And so what this allows us to do is this allows us to convert from moles to number of units. Or if we flip this, like say 1 mole of this contains 6.022 times 10 to the 23rd, then this will allow us to go from number of units to moles. Like say you have 3 dozen. Okay, so we can go from dozen to units. 3 dozen would be how many units? 36 units. Like that. So we can do the same thing here. So those are the, but they're showing more. We talked about the mole to gram conversion and the gram to mole conversion already. We need the molar mass. Molar mass is abbreviated MM in this case. For units to moles, we'll need Avogadro's, or for moles to units, we'll need Avogadro's. This is something called stoichiometry. Stoichiometry are quantity relationships. You know, so all we've been talking about are quantity relationships. Quantity relationship between mass, quantity relationship between atoms. That's all stoichiometry. So these are stoichiometry math. And so here is a gram to mole conversion. Here, gram to mole, and the moles to quantity. That is number. Or we can go from the number of particles to moles and back to grams. That's the map that we have so far. Determine the mass in grams of 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. Here I got 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. What's the formula for sulfur tetrafluoride? SF4. It's a binary molecular compound, SF4. We use that. SF4. So we have 3.2 times 10 to the 24 SF4. Is it molecular? Yes, it's molecular, so SF4 molecules. It's a lot of molecules. And so how much do all those molecules weigh combined in grams? Well, if we have the number of units, then we can convert it to moles. You know? Just like if we had 36 units, we can convert that to dozens. For atoms and molecules, if we have the number of units, we convert it to moles. We don't use a dozen as a counting unit. It's not very useful. And so we know that for every mole, there's 6.022 times 10 to the 23rd of those units. So a mole of SF4 consists of 6.022 times 10 to the 23rd SF4 molecules. So a mole of SF4 molecules. Usually we don't describe things to this extent, to this much detail. It's okay. And so the molecules, the individual molecules cancel out here, and we're left with the moles of molecules. And then we need to know how many grams. So we need to know how much a mole of SF4 weighs. We can figure it out because the sulfur, just go to the periodic table. We know what fluorine is already, but sulfur we can find out in the periodic table. What would you call sulfur?
32.07.
Yeah. And then we have 4 fluorines. So 4 fluorines, that's going to equal 4 times, and we called it 19.00 earlier. So this is 3207, and then 4 times 19 would be like 4 times 20 would be 80 minus 4 would be 76. 7, and then 8, 108.07. So there are two ways of reading this mass. A single molecule of SF4 weighs 108.07 U, whereas a mole of these molecules is going to be weighing 108.07 grams. Well, we're dealing with mole quantity. So we're going to get 108.07 grams of SF4 molecules for every mole of SF4 molecules. So typically it's written like this. Draw mole formally. Let's see what the value is. They rounded it different than we rounded it. Do you see how they rounded 32.06? So their molar mass is a little bit different than ours. We got 5.7 times 10 squared. I want to see how they round it, what the number is here before rounding. Excuse me. And so here I'll do 3.2 times 10 to the 24. It's a huge number of molecules. 3.2 times 10 to the 24 divided by 6.022 times 10 to the 23rd. Even though that's did I get it right? No, I think I got it wrong. 3.2 times 10 to the 24 divided by 6.022 times 10 to the 23rd. Okay, this, that's a huge number of molecules, but that's only 5 moles. 5.31 moles. So we take 5.3138 moles of SF4, and then how much does that weigh? Well, 1 mole weighs this much, so this is going to weigh 5 times as much. Times 108, 107. 574 point. Okay, we're allowed just 2 sig figs, so we'll just carry 0.2 grams, which would be 570 grams, 2 sig figs, or 5.7 times 10 squared grams of SF4. So I went out of order in the book. They talk about percent composition by mass later, but I just threw it all in to the heading composition. Percentages always, to calculate percentages, we do that. But if you have a percentage, we can convert it into a fraction. Calculate the mass percentage of chlorine and calcium fluoride. All right. You want me to do that, or? Yeah, or do you think all right, the calcium fluoride. We already did the formula for calcium fluoride. What was it again? CAF. So calcium, we go to the periodic table, and we're going to be doing this a lot. We're going to look at the periodic table. We'll call calcium what? Did I already do the mass? I already did the math, didn't I? But it's all right. We'll do it again. Calcium is 40.08. And then we have 2 fluorines. 2 times 19. 38.00. So this comes out to 78.08. We can leave the units off there. And so we need these numbers here, because this tells me how much calcium I have, how much fluorine I have. And so the percent calcium by mass is equal to 40.08 U or grams worth for every 78.08 U or grams worth becomes 100%. What does that come out to? 40.08 divided by 78.08 51.33% calcium, and the rest has to be, there's only two things. The rest has to be chlorine, so we'll do 100 minus that, so we need 48.67. 48.67% chlorine by mass. So that comes from 100% minus 51.33%. 100% infinite. Or 60. So they got 48.67% fluorine. They calculate fluorine first. Oh, actually, they were only asking for fluorine. So read the question carefully. Calculate the percentage composition by mass of aluminum sulfate. All right, first you got to get the formula for aluminum sulfate. So get the formula for aluminum sulfate. And then, let me know. Probably show the periodic table. You're always going to have a periodic table available, no matter what. You're always going to have a periodic table on the test. So what is aluminum? Charge on aluminum, variable or fixed? And what is it? Charge. 3 plus. And then sulfate. How many oxygens? 4. So 4, 2 minus. And so how many aluminums, how many sulfates do we need? 2 Yeah, 2 aluminums and 3 sulfates will balance it out. Al2, SO4, parentheses 3 aluminum sulfate. Well, the first thing is we have to calculate the total mass first. It's tedious. This is why I like to look them up, but we got to do it, learn to do it anyway. 2 aluminums. Aluminum, what are we going to call it? 26.98. The situation is, this is why you don't want to go 3 decimal places. It starts getting cumbersome. And so 2 times 26.98. Well, 2 times 27 is 54 minus 0.04 would be 53.96. 53.96 worth of aluminum. 3 sulfurs. It's going to be 3 times 32.07. So 3 times 32 would be 96.21. 96.21. And then 12 oxygens. 12 oxygens is 12 times 16.00. So 10 times that would be 160, plus another 2 would be 32, so 192. So the reason I like to keep these numbers like this is so I could try to do as much of it in my head as possible, then it's faster than punching it into the calculator usually, you know. So try to keep the numbers. And then 7, 11, that's done. 4, 10, 12, 10, 15, 24, 342, 17. 342, 17 if I didn't make a mistake. The problem is if I do it in my head, I'm more prone to making mistakes. So I get 342.17 total mass. This could be grams or U's. You know, typical units we're going to do are grams per mole. So typically I call this grams per mole, and then grams per mole. But anyway, we can get the percent aluminum. The percent aluminum is 53.96 grams of aluminum per mole. The units are going to cancel out over a total of 342.17. assuming I did the calculation correctly, I probably should check it. Did I do it correctly?
Yeah.
So, let's get the percent aluminum. It's gonna be 53.96 total. Let's, all the aluminum in this divided by 342.17 is 15.769. 15.769% aluminum. Okay, then we're gonna go to percent sulfur, which would be a total of 96.21 grams of sulfur over 342. If I, if I take one mole, if I take one mole, then I got 96.21 grams. Sulfur, 342.17 grams of aluminum sulfate, 100%. I carry one extra here just to see if it adds up to 100. Let's see, 117%. And then the percent oxygen, you have a total of 192. Looks like oxygen is definitely the most. 342.17, 100%. So 192 divided by 342.17. 56.112. Okay, now here's the check on this. These three should add up to 100%. I carry one extra digit, so I can try to lower the round off error. So let's see it. 15.769 plus 28.117 plus 56.112. Oh, it doesn't come out to 100%. It comes out to 99.998. Is that close enough? Yeah, yes, that's close. And in fact, that round to 100, so we're good. It just doesn't come out exactly because of rounding error. All right, we're out of time, so I'm going to stop here.